I know, right?
It's not a pasta.
That's 37.5. It's so thick.
It's a what?
Thick.
The marker?
Yes.
He wants to be thick. He wants to be thick. Everyone got higher.
Are you sure?
I thought it's Sir, I'm here.
Why?
5, 8, 18.
Wait. No, I got the exact same score.
Same.
37.5.
Oh, you're calculating the thing.
Yes, exactly the same.
So,
What version is your phone? Is it wrong? No, it's so sticky.
40 and false.
What's not?
It's wrong.
40. But then there should be 1, 2, 3, 4, 5, 6. Yes, yes. So okay, so let's pick up from where we left. So last time we stopped at. Let me go back to the book from last time first. Okay. Right, we stopped at like the difference between polar and non-polar bonds. Okay, so when we mentioned what the two cutoff values are, okay, what the cutoff value is for determining whether a bond is covalent or ionic bond. So today I prepared for you a like actually four-sided worksheet. Okay, four-sided worksheet. This is the first page. The first page. You can stay for it. This is the first and this is the third. The first. First and third. Okay, you can paste and stay on the back.
First in the table.
And yes?
Change it.
Oh.
You can have it. You can sell it to the library.
Okay. So can you put this down on the worksheet? Okay. So you can see there are 3 types of bonds below. So this is what I want you to fill out now. Okay. So write down the types of bonds. Okay. So types of bonds. We have 2 types of bonds in chemistry: the ionic and the covalent bond. Okay. So you can write this down on the notebook or on the worksheet actually. So on the left we have covalent bond, and on the right we have ionic bond. So this corresponds to what you see at the bottom half of the first page. You see the table. So under, do you have something to add? So under covalent bond we have 2 types of covalent bonds: the non-polar covalent bond and the polar covalent bond. So remember, polar means there is an uneven sharing of electrons. So this is what I wrote under. Okay, so you can put down the name of this bond in here. When you see uneven sharing of electrons, that's what we call a polar covalent bond. And when you see the word even sharing of electrons, that's non-polar covalent bond, because covalent bond basically means sharing. So whether you're sharing the electrons evenly or unevenly determines whether you have a polar or non-polar bond. So write down polar and non-polar means, so when you see non-polar means even sharing. So even sharing. Polar means uneven sharing. And which atom will get more electron? Do you remember from yesterday what does electronegativity mean? You can see at the top part of the page, I wrote down the term electronegativity. So you want to take our highlighter and highlight the phrase that says, it's the ability of an atom to attract electron in bonds. So when you look at this table, so I've calculated the value for you. You see the value increasing from left to right. Increasing from left to right. That means atoms on the right, they will attract electron more strongly than atoms on the left. So that's what electronegativity means. So what do we mean when we have even sharing? So you can see at the bottom of the table, there are 3 boxes for you to fill in an example. So I want you to put down one example of each type of bond now. Starting with ClCl, and then you have HCl, and finally you have NaCl. Only draw a line between ClCl and HCl. So don't draw any line between Na and Cl. Okay, so don't draw any line between Na and Cl. Okay, so you put this as the example for each type of bond. And I want you all to look up the electronegativity value for these atoms for me from the table and put it underneath these atoms. For example, where's chlorine? Chlorine is here. It has electronegativity of right now 3.50. So can you do this for the other example and tell me what the electronegativity value are inside those bonds? Okay? And then we will find the difference. So we can find the difference. So delta En means the difference in electronegativity. What's the difference here? 0. Yes, okay, so this is 0. What about the difference for the middle example? H and Cl, where's H? H is 3.04 up top. 3.5 minus 3.04.
0.46.
Yes, 0.46. Which you see is smaller than 1.8. So you can draw the cutoff line here. So this is the cutoff line. This is another cutoff line. When you have a bond with delta En smaller than 1.8, that's covalent. Okay, anything with delta En smaller than 1.8 is covalent. You see 0.48 is smaller than 1.8. 0 is also smaller than 1.8. But then what sets apart the polar and the non-polar covalent bond is another value, 0.4. So if something has electronegativity difference less than 0.4, it's considered as a non-polar bond. You know 0 is smaller than 0.4. But 0.48 is about 0.4. So this is why 0.48 is a type of polar covalent bond. So these are the 2 cutoff values you see. Okay, so cutoff values. Okay, for determining the type of bonds. And finally, what about the NaCl example? So look up Na from here, 2.15. When you subtract 2.15 from 3.5, what do you get? 1.35. Yeah, 1.35 here. Oh, maybe this. I think the Na here. There, I believe there is a mistake in here. Sorry. Okay, the value for Na. Yeah, maybe I picked the wrong table. Okay, sorry. It should be 0.9 here. I think some of the values here are kind of wrong. Yeah, I'll give you a revised copy on this page later. So this value is correct. So can you use 0.9 first? Okay. I think this table, for some reason, the values there are not right. I'll give you a revised copy next time. So this is right down 0.9. And let me correct the value for H from the previous page. Cl is actually 3.0. Okay, so let's change that. 3.0 and 2.1 here. So 2.1, 3.0, my bad. Yeah, it's just the table. So just the table. So this is 3.0, and can you take out y out and just change these values? Sorry. The first one is still 0, the delta En. But the second one will now be 0.9, and the third one will be 2.1. So you see 2.1 is above 1.8. So that means it is an ionic bond. Okay, anything with delta En greater than 1.8, ionic. Less than 1.8, covalent. But once you have a covalent bond, in order to tell whether it's polar or non-polar, you use another cutoff value, 0.4. Okay, so now we have a simple task on the back page. Okay, so use the values that I provide you on screen now. Can you also draw something in these boxes here? So in these boxes, these 3 boxes on the first page. You are going to use a highlighter to show the relative attraction for the electrons. You know, if the two atoms have the same electronegativity, it means they attract electrons just as well, right? That's what having equal electronegativity means, like a ball game. If the two players, they have the exact same, strength, the electrons are not particularly, distorted towards one side. What about in the middle example? Which atom, H or Cl, will attract electrons better?
CL.
Cl. So therefore, you should take out your highlighter now and draw something that looks like a pear. Okay, like a pear. Okay. Yeah, where the electron is like accumulating around Cl. This is like in a tug of war game. It's like a bit one-sided. So you see, it's a bit one-sided. Okay, this game in here, with Cl being the stronger contestant. Finally, you have such an extreme case that the electrons are basically transferred from Na to Cl. So you see this is still sharing. You see the electrons are still here. And this is also sharing. But this is even sharing. As the electrons is in the middle of the two atoms, this is uneven sharing when the electron is closer to Cl than it is to H. And this is not even sharing at all. This is the transfer of the electron. So can you put down the word transfer? Or transferring the electrons here. So the purple arrow there is showing you that electrons jump from Na to Cl. So do you see the difference between covalent and ionic bond? Covalent means sharing. Electron is still somewhere between the two atoms. For ionic bond, it's not sharing at all. The electron actually jumped from Na to Cl. Okay, so that's not sharing. So sharing means the electron's in the middle. And transferring means the electron went from one atom to the other. And so, how do we show the, so you can put down three different conditions then. Okay, so you can have delta En. Actually, I've summarized it for you in here, but let me put it on this page. When you have a bond with delta En less than 0.4, less than our first cutoff value, 0.4, it is considered as a non-polar covalent bond, you see. So this is equal to non-polar covalent bond. But if you have a bond with electronegativities between two numbers, 0.4 and 1.8, that's what we call a polar covalent bond. What if the difference is much larger than 1.8? Okay, so that the delta En exceeds 1.8. Well, we call that an ionic bond. So that will be called an ionic bond. So we have three different cases here. You cannot think of a fourth case because the delta En can only be smaller than 0.4, between these two values or larger than that. Okay? Even when you have delta En equals 1,000, it will still be in the third category, right? So this covers all the three cases. You cannot think of a fourth case. So these are the three types of bond we'll encounter in chemistry. So on the next page, okay, so I need you to show the HCl bond on the next page at the top part. And can you help me bracketify those values here? H, change the value to 2.1. Cl, change the value to 3.0. Okay, I'll give you a revised copy of just this page. Maybe it's best that you don't stay for it now. Okay. As I will give you a new copy later. Just the second page, nothing to add there. Okay, yeah. Or you can just fix the values. Then we don't need like another copy. So can you tell me which atom attracts the electron better? Cl. So right now, H is less electronegative, and Cl is more electronegative. That means, what's your conclusion? Cl attracts the bonding electrons in yellow more strongly. I will paint the yellow color on this diagram here, don't worry. More strongly. And this is what the bond looks like. Okay, so you have H and Cl, and then you have the electrons, okay, accumulating around Cl more than it accumulates around H. So which atom here has, more electrons than, is it H or Cl? Cl. So therefore we say it gives Cl a delta negative charge. Okay, so right now what delta negative means? Delta means slightly. Okay, it has a slight negative charge due to the accumulation of electron. Okay, so you can also say that delta negative means electron rich. It's apparently rich in electron compared to H. H is poor in terms of electron. We have another symbol that we can add as well. It's delta positive. Delta positive means it has a slight positive charge. And the slight positive charge is due to this atom, H, being electron poor. So remember the word electron poor and electron rich, okay? The less electronegative atom will become electron poor because it attracts electron less strongly, right? Yeah, if you attract electron less strongly, your electron will be pulled away by the stronger atom, right? So therefore you will become electron poor. The more electronegative atom, because it attracts electron more strongly, electron will spend more time with this atom, and therefore it will make this atom electron rich. So do you see the meaning? Electron poor, electron rich, and how it relates to the electronegativity of the atom. Whenever two atoms with different electronegative form bonds, okay, the less electronegative atom will become delta positive. The more electronegative atom will become delta negative. Is this part clear first? Yes. And we have to show something called dipole moment. Okay, so underline the term dipole moment. What does dipole moment mean? Dipole moment, you can write down di means two. Okay, remember dichlorobenzene, something like that, right? We learned about the naming. Okay, so means two. And what about pole? Pole means opposite charges. Okay, so opposite charges, the positive and the negative charge. So positive charge and the negative charge. And we draw an arrow. Okay, so a dipole is an arrow, always pointing from the delta positive to the delta negative atom. So from the delta positive to the delta negative atom. In other words, from the less electronegative to the more electronegative atom. Okay, so now I will show you the electronegative table. Okay, forget about the values on this page. Okay, I think I took the wrong photo from here. But then I will be showing you electronegativity on this table. Okay, you can use this to answer the question on this page here. So there should be another page that says task 1 on it. Okay, so on the top. So you will now have to use this table. Don't use the one on the first page. I apologize for including a table with wrong value. Use the values provided to you on the board. Figure out which is the less electronegative, the more electronegative atom, and also draw the dipole moment for these 4 bonds. Okay, only 4 bonds. I'll do the first one for you as an example. So with the first one, what kind of bond do we have? CCl. The task is simple. You find C and Cl from this table. Okay, where is it? C has a value of 2.5. Cl has a value of 3.0. So which means which atom attracts the electron more strongly? Cl. So therefore it will become delta positive or negative? Negative. Okay, so it will become delta negative. And C will become delta positive. So you can use a highlighter to indicate where the electrons are found more. Okay, like this. This is what delta negative and delta positive mean. What about the dipole? How do we point the dipole again? Do we point it from the positive to the negative or negative to positive atom? How do we point the dipole? Positive to negative. So that means we draw the dipole this way. That's it. That's what I need to do. Okay, I'll give you all 1 minute to finish this worksheet. First, let me go back to this table first. Refer to these values. Copy the electronegativity. people here. We are working on this together. Use the values on the form, okay, to determine the less electronegative, more electronegative atoms, and also draw the arrow making the dipole moment. That way there. Yeah, you may want to copy the correct value first, okay? Yeah, copy the values also onto the relevant atoms on this worksheet. Yes, okay, and then, yes, okay, if they are the same, okay, then you don't have to draw like any dipole in there because there wouldn't be a delta positive, there wouldn't be a delta negative, yes, okay, and that would be a non-polar bond. Okay, right, so 30 more seconds. Yeah, because it's just finding which one has a greater electronegativity, which one has a lower, and just draw the arrow. Simple task. If there are segments, it's a non-polar bond. So anyone who sees
Some more like
this one, yeah,
so it's partially negative.
also non-polar.
Yes.
Yes. Right, correct. Okay, very good. Yes, okay. Hopefully, we are on this page now. Okay. Right, so now, so I see many of you getting the correct answer, okay, especially for the second and the third one. The second and third one is actually, they are actually trick questions. So when you have N and Cl, when you look up the electronegativity, you see that they are both 3.0. That means there is not a more electronegative or less electronegative atom. In that case, the bond will be non-polar. So can you put down the word polar here? Polar means there is a more and there is a less electronegative atom. Okay, just like the Earth has North Pole and South Pole. Okay, so this is like a polar molecule because there's delta positive and delta negative end. The molecule on the right, or the bond on the right, is a non-polar bond. So this is a non-polar bond. So for C and S, it's similar. Okay, so C and S, they both have a value of 2.5, which means there is not one atom with more electrons around it. So this is also a non-polar bond. And finally, so we have FO bond. So this is FO bond. F has an electronegativity of 4.0. And O has an electronegativity of 3.5. Okay, yeah, 3.5. So that means this time, which atom will be delta positive and negative? F will be delta negative. Yeah, so we put the delta negative sign here, and the delta positive sign here, and finally we draw the dipole pointing this way. So this is what we do to find if a bond is polar. If a bond is polar, the electronegativity will be greater than 0.4 but smaller than 1.8, which is true for this example and this example. These two examples. Yeah, and if the electronegativity is any smaller, okay, it will be a non-polar bond. Okay, note that the atoms, they don't have to be the same for a bond to be non-polar. Sometimes two different atoms, they can have the same electronegativity, and that will still result in a non-polar bond. So is this clear? How we determine if a bond is polar or not first? We need to use the values, okay? But then you see task 2, okay? We have to talk about something else before we look at task 2. Let's go back to this worksheet, okay? On the other side, you see bond polarity and molecular polarity. So this is how we determine if a bond is polar or not. What about if a molecule is polar or not? So write down bond polarity. So you may want to put this on your notebook first. Okay, so a bond is non-polar if the electronegativity difference is smaller than 0.4. a bond is polar if the electronegative difference is between 1.8 and 0.4. So that's how we know if a bond, okay, remember a bond is polar or not. So what about molecule? How do we know if a molecule is polar or not? Well, first of all, we need to understand the molecular shape, okay? Molecular polarity is not the same thing as bond polarity. Okay, so molecular polarity is not necessarily the same thing as bond polarity. So not necessarily the same as bond polarity. Let me explain why. Can you think of some examples of molecule first? What is the first molecule that you can think of in your head right now? HCl, yeah, HCl. When you look at the molecule HCl, how many bonds does it have? One. So in this case, if the bond, the only bond in this molecule is polar, the molecule will be polar. Okay? What about when I have another molecule? Now I will give you my examples. Okay, so we have CO2 and H2O. So draw these two molecules here first. Okay, I mean these three: HCl, H2O, and CO2. In the first example, we have HCl molecule with just one bond. On the right-hand side, we have two molecules, each with two bonds. So we have an H2O molecule with two bonds. We have also a CO2 molecule with two bonds. Whether or not these molecules are polar depends on how the dipole is drawn. So let me give you the dipole directly. I can tell you that this is how the dipole points, as O is more electronegative than H. And which direction should the dipole point in here? If I show you the carbon and oxygen again, can you tell me when carbon and oxygen form a bond, it should point towards O, yes, so therefore this is how we complete it. We draw two dipoles. You draw a dipole for each bond. You don't draw something like this, okay? Because for every bond there should be a dipole, so this is incorrect. You have to draw two dipoles like this. And now, let me ask you a simple question. Have you all learned vector? V-E-C-T-O-R. In this direction, yeah, in math. In physics, okay. Do all of you do physics? No. Do all of you do vector in math?
No. Not there. We're circles.
Okay, well, then I think I know how to make this easy to understand. Think of them as like forces. Think of them as like forces. If you're pushing in just one direction, with nothing acting against you, let's say I'm pushing an object in one direction with nothing acting against me, the object will move, right? If there's nothing acting against me. So you can say, you can think of these as like forces acting on an object. Okay? If there's nothing that acts against it, this will result in a polar molecule.
Yes.
So this is analogous to you, let me put down, you pushing on something. Okay, so you pushing on a I don't know, wooden block. Okay, you know the block will move. So then the molecule we say will be polar. What about in here? This is analogous to two persons pushing on the block with the same amount of force at the same time at an angle. Would the block move?
No.
If they're pushing the block at an angle, the block will actually move. You can try, okay? But how do I put it? Okay, this way. Because you have to learn about vector. Okay, let me try. If you have, this is how vector works. If you have one vector, so let's call this vector A. If you have another vector, and when they ask you what is the sum of these two vectors, you just have to find the arrow tail and then the arrow head of the other vector, you connect them. This will be the vector sum. Yeah, maybe you have done this in physics. If you have done physics, then you must know this. Okay, and I think even if you haven't done physics, this is simple enough to understand. So vector sum of A and B would be you connecting the arrow tail of one vector to the arrow head of the other vector. So let's try this. What is the sum of these vectors? What is the sum of these two vectors? So the sum of these two vectors will be This one. The sum of these two vectors will be this one, right? What about with two vectors that do not point like towards each other like this? What about this?
This place.
Well, the nice thing about vectors is that you can move them however way you like. Okay, for example, you can transform this diagram into something that looks like you see. I'm moving it like this. Yeah, this is what's so special about vector. You can change the diagram as long as you're maintaining the direction it points. So what is the vector sum? Is it pointing up or down? Up. That's it. You just learn vector. Okay? So can you put down rule for determining vector sum? I need to lay down these simple like skills, okay, for you to know what is happening. So write down finding vector sum. So finding vector sum. What is a vector, you may ask? Okay, so a vector is unlike scalar. Okay, so vector has both a magnitude and a direction, right? So if you know both of these terms, right? Magnitude means the size of a number, like a number. Direction means where it points. So both a magnitude and a direction. Okay, and there are just two rules, okay, that governs how vector adds up. Okay, the first rule is to find the sum of vector. So to find the sum of vector, just draw an arrow. So just draw an arrow pointing from the arrow tail of the first vector to the arrowhead of the second vector. So from the arrow tail, so you call this the arrow tail. So this is the arrow tail of one vector pointing to the arrowhead of the second vector. Okay, so from the arrow tail of the first vector to the arrowhead. So now do this again. On the example H2O, can you tell me what is the vector sum of these two arrows? Right, so remember what I said, right? When you have two arrows that point this way, which doesn't look great, it's okay. You can just move them until you see them pointing head to tail like that. So what is the vector sum now? Pointing up. Yes, so this will be the vector sum. Okay? So if you have a non-zero vector sum, it is said to be polar. Okay, so this molecule here is polar. What about CO2? Does it have a vector sum? No. This is because if you imagine this as force now, it will be even more easy to understand. Imagine that two persons, they are pulling on this wooden block with the same amount of force. Not that they are pulling the block in opposite direction, but with the same amount of force. Will the block move? No, right? So all you agree that it won't move, right? So in this case, we say the two vectors, they have cancelled out. Because if you connect them, yeah, so let's do the thing we did just now. Okay, so we move the arrowhead, okay, to the, so that it touches the arrow tail of the other vector. When you draw an arrow pointing from the arrow tail to the arrowhead, does this arrow have any length? No. So this has zero length, right? So we say there is a net vector sum in here, so therefore it's polar. And if there's no net vector sum, it will be nonpolar. So CO2 is nonpolar as a result of this. Okay, I know these examples are not enough, which is why on the right I have some more. So can you take out the worksheet? You see three big boxes, okay, on this page. So can you draw the first molecule out first? We are comparing HCl with ClCl. So the first bond has a vector, so it has a dipole moment. The second bond has no vector. So which bond is polar? Which molecule here is polar? The top one, right? So write down polar and non-polar. So this is all that you need to draw in the first box. All that you need to draw in this first box below. HCl versus Cl2. Yeah, it gets harder. it gets harder. Okay. What about the second cell on the right? Okay, so CO2, so draw CO2 and draw H2O and show the two vectors like this. So can you tell me what is the vector sum in the, okay, yeah, you can excuse yourself for the bathroom. So when you look at the top example, do these cancel or do they not cancel? They cancel. They cancel. Okay, so therefore we say it is non-polar. Okay, so if the dipole moments cancel, so the dipole moments cancel, it is non-polar. What about in here? Do they cancel?
No.
No, they do not, because you can draw this diagram like this. Yeah, so this becomes this. And what is the net dipole? The net dipole will be pointing up, right, like you mentioned. Okay, so that means they do not cancel. If they cancel, there wouldn't be any like arrow pointing up at all. So we say dipole moments, the green thing means dipole moments. They do not cancel. And if they do not cancel, that will result in a net dipole moment. So the yellow arrow represents the net direction they are pointing. So net dipole moment. So what is the conclusion? It is polar, yeah. And, yeah, before we continue, you can try the last example here first. Let me draw it out for you. And I won't reveal the answer until the other students come back. So you can draw it first. What does CCl3 and CCl4 look like? You may also name it. Yeah, so apply the naming skill. How do we name CHCl3 and CCl4? So what do you call CHCl3? Trichloromethane, yeah. And then we have CCl4, right? What is CCl4? If tri means three, tetrachloromethane. Tetrachloromethane, okay, yeah, because it's really just an alkane. And use the electronegativity that I will provide to you now to figure out the direction in which the dipole points. Okay, I'll show you the values now. This is 3.0, this is 2.1, and for carbon, I have to look it up. Carbon is 2.5. So these are the electronegativity. Draw the dipoles. Okay, so this is the task you should focus on right now, and we'll continue with the rest of the class.
Josh,
Do you need back my power bank? What is
Do
it?
you have any test mixing?
Yes, organic chem.
Main subject.
Yeah.
How many is that?
Huh?
How many is that?
What's the main subject?
Wait, how many?
3.
Nothing.
No?
Nothing.
Oh, really?
Oh, math.
Math? What chapter?
The one we did before. I don't know the name.
What division? He won't even let me. You know the fucking the test. He won't even let me lay on the desk. Like, I can't finish it. Then just let me be. Like, try your best, and I'm like, no. What? Suffer.
So yeah,
What
you
part
can
did
go
you get?
dipole or inverse on the molecule, show how the weighting and inverse, and the rest of the quantity effects.
1, 2, 3. How many more you got?
And put down the name as well. You should know how to name it.
How many did you got? 6.
There's the forming test. I mean the organic chemistry test. So you have to know how to name these compounds. Right, yeah, please return your seat. I mean the other students are coming back.
In the next 2 periods. 2 to 55. And then 3 to 1.
The Chinese class starts at 4:30, so we'll go at 4:30.
How was yours ending at 6:30 when the school closes at like?
Because the teacher is an alumni of those universities.
Okay, so let's check the answer. Where should the dipole moment point for the CCl1? If these are the electronegative values, should it be pointing from C to Cl or Cl to C? C to Cl. Always point from the less electronegative to the more electronegative atom, right? Remember, the dipole moment always points from the less electronegative to the more electronegative atom. So ask yourself, C and Cl, which one is less electronegative? C. So therefore the dipole should point from C to Cl like this. So draw 3 of these. What about between H and C? How should the dipole point for H and C?
H towards C.
Yes, H towards C. Okay, so can you wait me? Okay, back me. Yeah, so, yeah, okay, we are back. Okay, class has resumed. Yes?
Turn off the airplane.
Turn off the engine. Okay, the remote is back. Right. Okay, so can you tell me if these dipoles, though, they will add up to result in a net dipole or will they cancel out?
Net.
Do they look like they will cancel out?
No.
No, because they seem to be a net direction pointing which way?
Down.
Pointing down. So sometimes you don't really have to add up the vector. You can trust your instinct. You see these 4 dipoles in green, they all seem to add up to point downward, right? You don't have to calculate what this value is, just have to, sometimes trust your instinct. They all add up to point down. What about here? What happens if you have 4 dipoles, each pointing towards a corner of the tetrahedron? Do they cancel out or do they not?
Cancel out.
They cancel out. When the dipole cancel out, write down this like the summary here. So the summary here is when the dipoles cancel out, so when the dipoles in green do not cancel compared to when they cancel, what will happen? Okay, so when the dipoles do not cancel, there will be number one, a net dipole moment. The net dipole is the thing in yellow. Okay, so there is a net dipole. So there is also a net dipole here. And there is also a net dipole here. But in the other cases, there simply are no dipoles, no net dipole. So here you have no net dipole because the two dipoles cancel. You have no net dipole because you don't even have a polar bond to begin with. And here you also have no net dipole. So there will be no net dipole. So what's the third conclusion you can draw? And it is that the molecule will be polar if you have a net dipole, and it will be non-polar if you have no net dipole. Okay, so put down this important conclusion first. We'll be using whether the dipole cancel out to determine whether there is a net dipole. And if there is a net dipole, the whole molecule will be polar. Okay, so if this is all too confusing to you, this is why I have prepared task 2 in here. So can you look at task 2? Okay, and let's draw these molecules out. Right, and let me teach you an alternative method, which will be very useful for solving the problems in task 2. Okay, before we continue, look at the alternate method down below first. If this sounds very confusing to you, don't worry, we have another solution. So the alternative method works like this. You may want to put this on the notebook as there will not be enough space on this page. So alternative method for determining if a molecule is polar. Okay, so determine if a molecule is polar. So how does this work? Let's take CO2 and H2O as an example. The first step is to consult that table and find the electronegativity of the atoms, okay, which they will give to you. Don't worry, you don't have to memorize these. I can't memorize these either, the electronegativity. So C, let's look it up. C is 2.5, O is 3.5, okay, so we take note of that. C is 2.5, O is 3.5. The first step is for you to assign a negative charge. So write down the steps, please. So step 1, assign a positive charge to the less electronegative atom and assign a negative charge to the more electronegative atom. So let's do this. Which atom will get a positive charge? Which atom will get a negative charge? Which atom will get a positive charge? Which atom will get a negative charge? C positive, O negative. Okay, so let's do this. We assign a positive charge here. We assign a negative charge here. Like that. So what is the second step? Second step is to find the center of the charges. So find the center. So I'm sure you all know what center means. You have one positive charge. What is the center of this charge? It's still where it is, right? It's still right on C, okay? But you have two negative charges. What is the center of these two negative charges? Right on C as well, right? So find the center, put it down. Find the center of positive and negative charges and see if they overlap. Okay, so negative charges. And check if they overlap. Okay, so the keyword here is overlap. If they overlap, the molecule is non-polar. Okay, there are only two possible outcomes here. If they overlap, then the molecule will be non-polar. So the molecule will be non-polar. If they do not overlap, the molecule will be polar. Okay, so write this down. We'll apply it on the example on the right. So if they overlap, the molecule will be non-polar. If they do not overlap, the molecule will be polar. Right, so let's try this. The center of the two charges will be here and here. You see they eclipse each other, right? Yeah, so you know they cover each other, they eclipse each other. So that means this is a case of them overlapping. So we say CO2 is therefore non-polar. So CO2 is non-polar because the charge centers overlap. What about H2O? Is H2O polar? Well, first we need to find the electronegativity. H, if I remember correctly, is 2.1. O is 3.5. So, can you tell me which atom should you assign a positive and negative charge to respectively?
H and
H would get
O. Positive.
positive. So can you do this? Okay, so put the positive charge where H is at, and put a negative charge where O is at. Where is the center of negative charge? Right on O, right? Yeah, because there's only one negative charge, right? So you put the negative charge on the O. What about the center of the positive charges? Somewhere in the middle, right? Here. So does it overlap with the negative charge center?
No.
No. So this is the second case. The charge centers do not overlap. You see, they are not overlapping. Here, they overlap. So we say H2O is polar. So if you find the vector method very difficult to understand, this is the only other method available. Yeah, is to find whether the charge centers overlap. And now I want you to apply this method on to solving this problem in task 2. Okay, so starting with CH4. So let's do this. We have C. Does anyone remember the shape of CH4 molecule?
One spacing out.
Okay, I see you're trying to describe the shape. You're not naming the shape. Okay.
Oh.
Tetrahedral. Tetrahedral. Okay, so write down tetrahedral. Okay, now I will give you the electronegativity. Okay, so these bonds point this way, the dipoles.
Fine.
Okay, so you can use the first vector first. If C is more electronegative than H, okay, how should you draw the dipole? It should be pointing from H to C, yes, H to C. But actually, CH bond, they are not polar bonds at all. Because the electronegativity, when you find it, what is the electronegativity difference between C and H? So H is 2.1. C is 2.5. So C is 2.5. So that means the delta En is just 0.4. Okay, so CH bond is not polar. Okay, so can you put down CO is polar? Because the difference here is larger than 0.4. Okay, so 1.0 is larger than 0.4. OH bond is also polar. Because the difference here is even more. It's 1.4. Okay, so 1.4 is of course larger than 0.4, so it's polar. But what about the difference here? It's 0.4. 0.4 is too small. Remember the cutoff value on the previous page? If you have like a bond with electronegativity equal to or smaller than 0.4, it is considered as a non-polar covalent bond. So without thinking, you can just say CH4 is non-polar. Because CH4 doesn't even have a polar bond to begin with, so it cannot be polar. Okay, so it is non-polar, we say, so CH4. Okay, if you do not have polar bond, you must be non-polar. Okay, let me draw you this flow chart in here. Put this down on your notebook. Okay, this will be how you decide if the molecule is polar or not. So first, you need to check if the molecule has polar bonds. So does the molecule have any polar bonds? So does the molecule have any polar bonds? So you will ask yourself two questions before you can tell if the molecule is polar. So to this question, you will get two answers. If you say yes, okay, yeah, there is polar bond. Yeah, so there is at least one polar bond. So one or more polar bonds. Then you need to ask yourself a second question before you can tell if it's polar. However, if you already answered no to the first question, you can immediately jump to conclusion and say, well, it is non-polar. The molecule is non-polar. If you answer no, there is not a single polar bond. So there is not a single polar bond in a molecule like CH4. So we say the molecule is non-polar. So what about when you answer yes here? Okay, well you have to ask yourself just one more question. The second question is, do the dipole moments of these polar bonds cancel? So do the dipole moments of these polar bonds cancel? And to this question you will get two possible answers. Okay, so on the polar bonds cancel. So if you answer yes, they cancel, then the conclusion will be that the molecule is still non-polar. Okay, so yes, they cancel. And if you answer no, they do not cancel, then the molecule will be polar. Okay, so it seems like a very complicated table, right? But don't worry, I'll give you an example. Okay, 3 examples, then you will know when each case is applied. So the molecule is polar. Okay, so let's look at how we use this table to find the answer. You need to copy this. Okay, this is not on the notes. Okay, so you need to copy this. And I will be copying this 3 times, and I'll show you 3 molecules. That would give us different answers. Okay, when we apply this table. So let me move this here and say it first. Okay, the first molecule I want to discuss with you is CH4. So is CH4 a molecule with a polar bond? What is the bond found in CH4? CH bond, right? Yeah, so you all find CH bond. So look up CH bond on the electronegativity table. C, like I said, has electronegativity of 2.5. H has electronegativity of 2.1. That means the electronegative difference will be 0.4. So is this a polar bond or is it a non-polar bond? It is a non-polar bond. Okay, so right now, because it is very, very small, we say this is a non-polar bond. So can you answer the first question first? Does this molecule have any polar bond? No, we just said this is a non-polar bond, right? Yeah, so that means to the first question, what would you have answered? Is it yes or no? No. That means you immediately jump to this conclusion here and say, well, yeah, the molecule is non-polar. We say CH4 is non-polar. What about when you have a molecule that looks like this? CO2. We look up the electronegativities again. So we have CO bond in here. C has electronegativity of 2.5. O has electronegativity of, I think, what is it, like 3.5? Is it 3.5? Yeah, 3.5. So what is the electronegativity difference? 1. Is 1 greater than 0.4? Yes. So this is a polar bond. So polar, it's very logical, you see this process, okay? You need to check the logic here. So if it has polar bond, what would you have answered to the first question? Yes. So therefore we are here. And the second question, do the dipole moments cancel out, okay, each other? Let's find out. How do we draw the dipole moment if C has a lower electronegativity than O? Towards O, right? So now your question is, do these dipole moments cancel? Yes. So therefore you answered yes to the first question and yes to the second question. Which means, what's your conclusion? The molecule, is it polar or non-polar? Non-polar, right? Still. Yeah, so this is what I meant. In the exam, you need to use this table, use this flow chart to get to your answer. So this is your answer for the first one. This is your answer for the second example. What about the third molecule here? Let's try this on H2O. Okay, again, I will be giving you the electronegativity, which we already have seen before actually. This is 2.1, this is 3.5. Can you tell me what's the electronegativity difference? What is the electronegativity difference? 1.4. Is it a polar bond? Yes, because it's larger than 0.4. Okay, so we say this is polar bond. So what do you answer to the first question? Yes. What about the second question? Can you show me how the dipole points first? Pointing, is it from H2O or O to H? H2O, yes. Do they cancel?
No.
No. Okay, so therefore what will you have answered to the second question?
Oh.
Do they cancel?
No.
They do not cancel, yes. So therefore your answer will be yes to the first question and yes to the second question. So what's your conclusion?
Oh.
It is polar. You see? Yeah, so write down the conclusion for me, please. Okay, we say CH4 is, and you need to use this on these examples now. Okay, yeah, I'll draw it for you still. Okay, so this is non-polar. Maybe I'll work with you on the first or second example, and then the rest you're on home. Okay, so we say CO2 is non-polar. What about H2O? H2O is polar. Do you get what I'm saying? Yes. Okay. So CO2 is non-polar. H2O is polar. CH4 is non-polar. Right. These are our conclusions. So let's try this. Does everyone understand what is happening now? You need to remember the table on top. Okay. But I'll keep on showing you this table. Don't worry. Okay. But then can you try the next example? NCl3. So we are building on what we learned earlier. Can you first draw me the structural formula of NCl3? Knowing that Cl is from group 7, N is from group 5. What is the first thing we do? We add up the outermost shell electrons. So what is it? You see, it gets harder and harder because you need to remember what you learned from the last lesson. From which lesson? Do you remember this page? The math part, this page. You need to do this now. So can you do this on NCl3? Okay, knowing that N is from group 5, Cl is from group 7. So what is the answer to step 1? 26, yes. 5 plus 7 times 3, 26 electrons. So this is the number of outermost shell electrons. What is the next step? 32, yes. Okay, very, very clear. Okay, some of you are very clear. So number of outermost shell electron. You see, you still have to remember things you learned from before. Just like at this point, you should still remember what 1 plus 1 equals. It is expected, okay, this understanding. So can you put down step 2? Is the number of outermost shell electron when stable. So we do 8 plus 8 times 3, which is 32. What is the third step?
32 minus 3.
Yes, which is 6. How many bonds does 6 electron translate to?
3.
3 bonds. Very clear. Okay. So when stable. So step 3 is where you subtract the two numbers. Okay, so we do 32 minus 26 gives 6 electron, which translates to 3 bonds. We are finding the number of bonds. And last but certainly not least, we are finding the number of lone pairs. Okay, so how do we find lone pairs? Which two answers?
1 minus 3.
26 minus 6.
Yes. Okay, very clear. 26 minus 6 gives 20. 10 lone pairs. Excellent. Can you draw out the molecule showing in your diagram only 3 bonds and 10 lone pairs? So I need to see this now. Draw out the molecule. NCl3. Which atom do you think is at the center? Yes, nitrogen. Usually it is the atom with a smaller number as a subscript. You see N has just as 1 as a subscript. Cl has 3. So N must be at the center. Yeah, you can put them in any position. You can put them at 12 p.m. position. You put like one of the Cl. Yeah, it doesn't change the answer. I want to see where the 3 bonds and the 10 lone pairs go. So that you can satisfy, yeah, so draw it. We'll check the answer in 30 seconds. Yeah, give everybody a chance to work with numbers. You know, there aren't many different positions to put 3 bonds. So this is where these positions are where the frequency. What about the 10 lone pairs? How do we fit the 10 lone pairs? How many on each CL?
3.
3 on each CL. Very good. Okay, so draw 3 on each CL. You know, 3 times 3 gives only 9. That means there's one lone pair left put on and. Yes. But you see, we don't stop here. What do we call this formula again? We call this structural formula. We would want to apply the VSEPR theory we learned last time. What does VSEPR theory predict? Can you tell me how many domains there are around the central atom? There are 4 domains. The first domain, the second domain, the third, and the fourth. So how do you fit 4 domains, do you remember? What is that shape like?
Trigonal pyramidal.
Yes, trigonal pyramidal. Very good. Okay, so can you draw this first? And then you put down the lone pair here. So this is where the lone pair is at. Remember the lone pair looks like a ghost. Okay? And then you have nitrogen here. And then you have Cl, Cl, Cl. So these are where you put the free bonds. What do you see when you consider only the bonding pairs? You see the shape trigonal pyramidal. You see? Do you see how we go from here? Well, we can learn a lot just by looking at the formula. From here, we got to the structure. So draw this and write down the shape. Write down the name of the shape. Trigonal pyramidal. Do you see what DSE expects you to be able to do? They expect you to be able to go from just this formula, NCl3, to here. And we did that. Okay? Well, yeah, a round of applause to all there. Okay? So pyramidal. You see, you went from just this term to here. Now, we need to build on that. We are not done. You have NCl3. Now I will give you the electronegativity. We apply what we just learned today. N and Cl. I will give you the electronegativity. Give me a moment. So N is 3.0. Cl is also 3.0. Okay, so we can put down N is 3.0, Cl is 3.0. Are there any polar bonds? No. So what will you answer to the first question here? Does the molecule have polar bonds? No. So, boom. Okay, this is a non-polar molecule. Done. You see now, in chemistry we have to make predictions. When they ask you, is this polar? Now you have the conclusion. You see NCl3 is non-polar. Because it doesn't have polar bonds. Can you see that the difference here is kind of small? Okay, it's not kind of small, it's 0. Okay, so the delta En is 0, which means it must be a non-polar bond. Pretty intense, right? So, we'll do the next one together. Okay, yeah, so can you try OF2? OF2, try OF2. The 5th example in under task 2. Okay, OF2. Again, I expect you to go through the same steps again. Okay, so if you're not sure what to do, look at the screen. Okay, we have these same steps. I will give you all 2 minutes because I know that's a lot to do. Okay, so you have OF2. I will give you the group number though. The group number of O is group 6. F is group 7. Okay, so we'll do this together. I mean, you will do this yourself first because I can't keep on doing every question with you together. I'll walk around to see if you are. So apply these 4 steps on OF2. Yes. Usually when we draw it like this, these 2 things will be on the same plane as the paper. We usually draw it like that. And then this one pointing at 5 or 4 p.m. position will be pointing out, usually. and the one at the back like a tree. Yeah, here, trigonal pyramid. We don't just say pyramid. For OF2 is not pyramidal. Yes, V shape. Okay, we will be able to test. But make sure you get this outline first. So do the calculation. If you aren't sure, like use the calculator. Okay, don't do it in your head. Okay. Can you please work on the people? In the next class. Can you please work on the people? How many units do you get at around? Four. That means you should fit them in those four things and then figure out what the shape is if you look at only the one.
How many bonds behind the triangular bond? And also two lone pairs, so it's 4. The lone pair are invisible.
Okay, I see at least one correct answer. Okay, when I walk around. Okay, actually there are more than one. Okay, correct answers. I mean more than one of you got the correct answers. Okay, so let's do this together. You tell me the answer. What should we write for step 1? The answer. 20. So write down the steps if you don't know how we get to this step. 6 plus 7 times 2 is 20. What about step 2? 24. So 8 plus 8 times 2 is 24. The first step. 4. 4, yes. This is where some students make a careless mistake. Okay, so you assume there are 4 bonds. There are only 2 bonds. Yes. And for step 4, 16, which is 8 lone pairs. Now show me the structures. Show me the structure of this molecule. You only use these 2 information to plot or to draw the structural formula. What does it look like?
V shape.
Yes.
How?
Okay, let me put down the O and the F first. You tell me what should go around the O and the F. What goes between the O and F?
Each has a
Yeah, 1 bond E on each side. Where do you put the remaining 8 lone pairs?
3
3, yeah, on each fluorine, and how many on the central O?
2.
2. Okay, good job everyone. Okay, so now apply VSEPL. This is the trickiest step.
I don't like this.
Well, you have to overcome your fear. Okay, you have 4 domains here. If you see 4 domains, you must draw something that looks like this. Okay, and then, but then you don't call it trigonal pyramidal this time. Why? Because they are not 3 bonding domain and 1 non-bonding domain anymore, but instead 2 lone pairs and 2 bonding pairs. So you draw it like this, and then you put the O in here, and then you put the F in here. Finally, which part of this molecule can you see? A V, yeah, I hear the word V shape. So can you highlight or draw a boundary around the part that you can actually see? This looks like the letter V. So this is V shape or band. But we are not done. Like I said, we are far from done this question. So we have OF2. So now you see, it's not a matter of choice. Okay, whether you put OF2 like this or like this. If you draw it like this, you're wrong. Because you just predicted that it is V shape. So don't draw the O and the F horizontally. Well, I know I did here. This is structural formula. Structural formula is actually not a very accurate formula. It doesn't show the shape faithfully, you see. So can you put down a more like a disclaimer here. So structural formula do not actually reflect the shape. Okay, so they do not reflect the actual shape. So they do not reflect the actual shape. So just because I drew the OF2 like this, doesn't mean OF2 is a linear molecule. You have to be careful. Only after you apply VSEPR, write down VSEPR here. Vesper or valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Okay. No. Okay. Now, okay, look at the electronegativity and answer the question. O has electronegativity, I forgot, but F is 4.0. What is the electronegativity of O? It's 3.5. Okay. So can you tell me if O is 3.5 and F is 4.0? Is this one polar? Is it polar? Yes, it's polar because it's larger than 0.4. Okay, so we say it has polar bond. What will you answer for the first question? Yes, there is one or more polar bonds. Now you ask yourself, okay, how do you point the dipole? O to F or F to O? O to F. Do they cancel? No. So if you answer yes, they are polar bonds for the first question, and then you answer no, they do not cancel. What's your conclusion? Polar. OF2 is polar. Done. Mission accomplished. Okay. Yeah, you should find this very, very rewarding if you can get the answer. Okay, yeah, because you just went from having a formula to making this deduction. That's what we do in chemistry. We predict, okay, we make predictions, okay, with limited information. So write it down. OF2 is polar. Yeah, we make prediction, okay? So OF2 is polar. So make sure you put this down. Okay, next up we have, so for the other one, I will ease your pain. For the other one, I will draw it for you, okay? Can you draw PCl5 now? Okay, draw PCl5. Yeah, I'm saving you the trouble of drawing it from scratch. So just draw it for me first. PCl5, SF6. And you just have to tell me whether they are polar or not. So I already helped you finish the first 4 or 5 steps. You're starting from step 5 here. Okay? And then you put back PCl5 on the worksheet. This is SF6. And then you have HF. For HF, I'm sure you know how to draw it. Okay? Everyone knows how to draw it. Okay? Just HF. Okay? And HCHO is a little bit more complicated. It's HC_OH. And finally, we have BF3. Now, I will be showing you the, what is that? The electronegativity table. And you help me determine if the molecule is polar. This part you do it yourself. I can give you all the answers. Okay? So let me find the electronegativity table. Okay. Right, so your turn. I will give you all 2-minute talk. 2-minute talk to determine if these molecules are polar or not using the electronegativity. Okay? So remember, when the electronegativity is smaller than 0.4, it will be a non-polar bond.
Too small so I can't see.
Right, yeah, you will have answered no to the first question, and the conclusion must be that the molecule is non-polar. If the electronegativity is larger than 0.4, it will be polar bond. Okay? Yeah, so therefore, 2-minute talk. Okay? I think it's large enough. Okay.
Sir, so big.
I don't want to zoom in further because if I zoom in further you cannot see. Oh, can I just cut that part off?
Can you do glass?
Disney Plus.
Yeah, this one.
You can just Google it.
They will give you this table. It's just that I gave you the wrong table. But this is the correct
Find
value.
out the polarity of the
Okay,
bond.
put a cross over here.
Then if there's a polar opposite, then it's almost $8.
Example 4 here.
That
Find
whole
X,
P
and you find X. Subtract them. 4 minus 2.1 is 1.9. 1.9 is greater than 0.4. It's a polar bond. So you need to show where the dipole points. Does it point from H to F or F to H? H to F. Always point from the lower value one to the higher value one. Okay, so draw an arrow here, pointing this way. Okay?
polar bond.
I'm at school. Am I wrong though? It's also polar, right?
Question where you
That is.
Wait, HP is polar.
Is Asia polar? This one.
Haven't done it.
It's polar. What's
PCL5.
If the value to be 1.9,
It's non-polar, right?
It's polar.
so therefore it will point. When you move forward,
Wait, it's above 1.
3 point the arrow will point from the center to negative and on H.
Since they look like they do. Why? Wait,
So we have to draw the arrows.
Yes, yes.
biology.
Yes. So maybe one more minute because you have to also draw the arrow. You don't just come to the
You
point.
didn't give up chemistry. CL, blah, blah, blah. You should have notes for the one that does that by side. It's a good thing I didn't jump by you. Back up.
Let's do
You need to draw the whole.
Why did you draw?
Perfect.
But not
Yes.
because
Okay, so I got.
this would be right off.
Oh, this one you need to do it separately. CH, CH, CO. Yeah. So just now when I walk around, I already see one perfect answer. Perfect answer. Okay, in everything. Let's see, let's see.
Sir, if this is 3.1, what will happen?
Oh, you don't subtract it free from one another. You need to do it two ways. That's CH, CH, and CO. You're not subtracting C from H from O at the same time.
Oh, so this is plus the other.
So you need to do it
Friday.
separately.
We'll just go to one.
Correct. Correct. Just go to one. Yes, the ones you have done so far, they are correct.
I'm getting ready.
Yes.
I got it.
Oh, you look at the direction to see if they are pointing out. If they are all pointing out, if they are radiating out, they cancel
Where are
out.
you even at?
Yeah. Okay.
7 more minutes.
Okay, right, so let's check the answer. I congratulate the student who got a perfect answer. So let's learn, okay, like how to draw it first. So when you look at P and CL, what is the value of electronegativity for P and CL? So P is 2.1. So P is 2.1, CL is 3.0. That means the dipole should be pointing from, is it CL to P or P to CL? P to CL. So we draw it 5 times. So we draw destroy 5 times. Do these cancel out?
Yes.
Yes. If you see arrows radiating outward or inward and they are symmetric, it's most likely non-polar. They most likely will cancel out. So the conclusion is that PCl5 is non-polar. What about SF6? When you look up S and F, F is 4.0, F is 2.5.
Towards
So is it from S to F or F to S?
SF Express.
So is it S to F or F to S? S to F, okay. Right, S to F. So do they cancel? Yeah, well this one you should be able to see why it cancels. This one you should be able to see clearly why it cancels. This and this will cancel out. This and this will cancel out. And this will cancel out. So everything cancel out. When the dipole cancel out, what's the conclusion?
Non-polar.
Non-polar, yes. F6 is non-polar. Okay, what about HF? HF is it polar or non-polar? Polar. Okay, and just now Sarah raised a question. Not sure if all of you have seen, maybe none of you don't think. When you plug the value in, what is the difference?
It's 1.9.
1.9. Do you notice something odd? 1.9 is very large in the electronegative difference. Yeah, you will think that it is ionic. Okay, yeah. So this points us back to this page. Okay, that these two values, they are not very trustworthy. They are just for reference only. Okay, so 1.9, you may think that it lends itself into the territory of ionic bonds, but actually HF is still covalent. Okay, yeah. So these values are just for reference only. They are not all that accurate. Okay, like roughly 1.8, roughly 0.4. And in exam, don't worry. When they give you a HF bond in here, it must be covalent. If you see a bond in here, it must be covalent. Okay? So, but then where should the dipole be pointing? H to F. So is this polar or non-polar? Polar. So HF is polar. And second last example. Well, this one is where a lot of students make mistake, I see. But don't worry, learn from the mistake this time. You need to do it 3 times. What do I mean? So you have C, you have H, you have O. Okay, so when I walked around just now, I saw that some students would subtract these 3 numbers from one another. You don't. You need to do it 2 at a time. What I mean is, when you look at CH bond, you first look at CH bond, you find the difference. Is it polar or non-polar?
0.4.
0.4 is actually not like it is actually non-polar. Okay, yeah. So therefore, you actually do not need to draw.
If it's double bond, do we have to like?
Oh, double bond, just ignore it. The double bond is just showing you how strong the bond is. It doesn't show you how the electrons are distributed. Okay? Yeah. So if you see a double bond, then just keep drawing double bond. You don't have to change your calculation because of the double bond. So and for CH, you can draw the dipole like this, or you can just skip the dipole altogether because it's actually not a polar bond at all.
It is. It's 0.4.
If it is smaller than or equal to 0.4, it's non-polar. Yeah, that means you don't need arrow. Okay, so non-polar bond means no arrow. Okay, polar bond means arrow. But if you drew an arrow there, I will forgive you. Okay, it will not affect the determination of the answer. What about CO bond? What about CO bond? CO bond will be polar, okay? Because when you calculate the difference, what is the difference? 1, yes. So CO bond is polar. So write down CO double bond is polar. So where do we point the dipole? How do we point the dipole? Up, okay? So is there any other dipole to cancel this out? No. So what is the conclusion? Is it polar or non-polar? Polar. Okay. Remember, non-polar means all the green arrow cancel out, so that nothing remains. Like in here, you see the green arrow, they all cancel. That's when you say it's non-polar. Here, nothing cancels out with this green arrow. Nothing cancels out with this green arrow. So HCHO is polar. Finally, CF3. BF3 is non-polar. Why is that? Because B has a electronegativity 1.5, F is 4.0. So what is the difference? 2. So the difference is 2.5. Yeah, which makes you think that it is ionic again. I know, yes, but don't worry. I can tell you that the most response is that they are polar. So how do we draw the dipole? B to F or F to B? B to F, okay. So does it look like these dipole will cancel or will they not? They will cancel. Usually when the arrows they radiate outward or when they radiate inward in a very symmetric manner, they cancel. They cancel. And sometimes you can trust your instinct. I don't know how to explain this to you, but on the textbook, they compare to like this physics example. Imagine there are 3 guys pulling, okay, on a like a rock, okay, at the center of these 3 persons. They are pulling on this rock with the same amount of force. Okay, will the rock move an inch? The rock will not move an inch. Yeah, so this is the only way I can tell you why this is the case without going into some physics concept. Okay? But then,
law.
yeah, like Newton's law. Okay, so here, what is the conclusion? BF3
is non-polar.
non-polar. So do you all get task 1 and 2? It gets harder, you see. So and you see, this is why it's so important to do revision on step 1 to 4. If you get a mistake, no matter how small the mistake is in step 1 to 4, you see it magnifies. It will just make all the answers downstream wrong. So this is why I need to build a stronger foundation here. Okay, you need to be very good at doing this. Okay, so practice. Okay? Is this clear? Yes. I want to show you what will happen if we draw PCL5. Because if you apply these 4 steps on the PCL5, you know something will go wrong. Let me show you. Can you do this now? Okay. Because I want to teach you how to troubleshoot. You don't just look at a problem. Oh, I messed up. Okay, yeah, and then you don't know how to fix it. Okay, I'm teaching you how to fix it. Yes. So you see, if you haven't been revising, you are maybe you have to catch up. Okay. So that's how I would put it. I wouldn't put it that way. So can you put down? We have the quiz, not quiz, test. It's a test on organic chem next
Friday.
No.
Friday.
Next
Wednesday.
next Thursday. Next Thursday.
Next Thursday.
This coming Thursday. Okay. So,
See you in the next one.
okay. So this.
Year.
Okay. Let me finish this first.
Organic chemistry is like 10
It's
seconds.
Okay. Right. So I don't have the exact time because
21 to 25.
okay, 21 yeah, all the organic chemistry.
Their quiz is like
Handwritten.
they
Let
give
me
it,
double check. Let me double check.
they give it
20 to 23.
they memorize it.
Yeah, like Master Chef Australia.
They don't like quiz books.
You have to theories. You have to memorize.
Just a moment.
Do what Patrick does. It's all takes calendar where they either work together.
Or just
You don't just need an estimate.
Just
their
a
quiz is
second.
their quiz is
It's 20 to
memorize
23.
and then make it.
20 to
Memorize
23.
it, yeah.
Fossil fuels and carbon compounds.
Yeah, and
Okay?
then-
You have to review its naming. I can tell you that there will definitely because I remember you did quite well in naming. Yeah, but everybody should revise naming. Okay? Yeah. Okay. So back to here. Okay, we are not done. Okay, let's not get so excited. So can you help me figure out the answer to this question, PCL5? You will discover that something has gone wrong if you do this. So do this now.
PCL5.
PCL5. Yeah, I'm giving you the formula. I want you to just do what you normally do. Find the structural formula. You will discover that something was gone wrong. And I want you to tell me what has gone wrong.
Is it not documented?
Find the answer first. You will know. Go through each step.
What's the thing for CL?
P is from group 5 and a CL is from group 7. You have 5 chlorine and 1 phosphorus. Yes?
The camera is not focusing.
Oh.
Oh. It's okay, we can listen.